Okay, example 10. Example 10, you look at the diagram. This one is a circular body. You have omega, you have alpha, you have R, you have 2R. One is an inner circle, one is outer circle. So this is a pulley with a two circle. The rope was tied to the inner circle. All right, and you're referring to 2 points, A and B. Okay. Yeah, so this is a very important example for your incoming test too. So the spool unveil the chord such that the instance show that has an angular velocity given and angular acceleration given. Determine the acceleration at point B. All right. Now, how do you solve this question? Again, you have two methods. We use vector. So if this one rotate this way. So okay, this one was given like this. Okay, the first one is you find the acceleration first. You convert acceleration with alpha r. So alpha r is given here, alpha r. So you focus from G, focus from G, then you use your r.2, referring to point A. Okay, referring to point A, you get your acceleration from the gravity. Okay, then after that, you apply equation of motion. Right. So you draw kinematic diagram. Your focus is on point B. So from G to B, you draw a R, and then you know that this one rotate this way is a circular motion. Circular motion, you have you can convert your acceleration into a few directions. One is normal, one is tangent. However, in this case, we use vector analysis. Vector analysis, we focus on x and y and not normal and tangent. So here, we try to estimate where is our acceleration by splitting our component of A into x and y at D. Then your AG, you find just now, AG pointing this way, right? So you take the acceleration equation that you learned in the previous class, right? So it already derived this equation. So AB equal to A plus alpha cross R minus omega square R sub B. You substitute the value, so you change the equation a little bit. The previous one, the A, you change to G, A you change to G, A you change to G, then you split because we are using vector analysis. So AB, you split to I and J, this one. Because you don't know where's the direction, you just split to X and Y. Then AG, you know, go down. Okay. Then alpha, this way, but Y negative. Use your right hand rules again because you're in rigid body chapter already. Y negative because your alpha this direction, so your hand was curved in like this, and your thumb was pointing inside the screen. So if your thumb pointing inside, it becomes negative. If your thumb pointing outside, it becomes positive. All right. So in this case, your K for your alpha, sorry, not alpha, for your omega. So in this case, G. Sorry, this one is alpha. Alpha minus 4, and it's negative because it's pointing in. Direction going in. Cross RB stroke G is 3. This one, 3. And omega is 3 again. So it's negative because it's going in. You square it. Then R is 0.3J. You balance the I and j together, you'll get your bx and by. Bx is to the right positive, by going up. Then this is a vector. So square this one plus square this one, square root, you get the magnitude. And then you find the tangent, inverse tangent, you get the theta of your acceleration. Okay. All right. Then what about the scalar analysis? Scalar analysis, you draw the normal kinematic diagram, where here you have a normal and tangent direction as you normally do for your circular motion. There are two methods. Now it's method number 2. So at point B, you know that if this one rotates this way, you have a tangent and normal direction of your acceleration. Okay. So what is the definition of a normal acceleration? Omega square r. The tangent one is alpha r. Fixed already. Delta 8, correct? Yeah. Okay. Okay, the balik already, the one that I write on the whiteboard, the balik already. The T tangent is alpha r. The normal acceleration is omega square r. Yeah, the one that I write on the whiteboard, the balik already. So memorize this one. Okay, so then the r was given. You can calculate from the diagram. You write the normal acceleration equation or vector equation. AB equal to AG plus the AB stroke G component. So you break the relative acceleration into tangent and normal direction. Okay. Then you break into xy. Okay, you break into xy. AG going in plus gradient. Okay. So you have two directions. Then you look into x direction, you group them together. You look at y direction, you group them together, you still get the same answer. Okay. So, okay. Then another one. This one is the link system or piston system. So the question asks you to find the acceleration of piston at the instant AB at the position shown. You're given the omega AB and omega BC. And the crankshaft turn in the clockwise angular acceleration, you're given the alpha 20 radian per second squared. So here you have a fixed link AB. The alpha omega for AB was given, and then link B to C also given. So you're seeing a triangular. So this one, you know that sometime when you see this kind of diagram or picture, you know that this one you should recall cosine rules. Straight away you draw a cosine rules on your answer sheet there. Then it will remind you to use cosine rules if needed. Okay, so you draw kinematic diagram. So it's quite direct. So how to do kinematic diagram? You look at the motion of the object. So kinematic means you deal with velocity and acceleration. So this one C, we know that this one was fixed to one direction. It's either move up or move down. So if you imagine, if you move this link AB clockwise, if you move clockwise, this point C will going to move up, right? Right. If you turn AB clockwise, this arm will push this C point up, right? So your C point can only move up or move down. So logically, C will be, you put positive go up. That you predict it will move in a positive direction, go up. Why? So you draw in your kinematic diagram, you draw AC, acceleration go up, or you can draw V go up also can. Then the rest is you just copy. Right? The rest is just copy, nothing new. It's only that you need to be careful. You need to calculate the distance between here to here, or the link between the x here, and until b, 0.25 cos 45, we get the length of this one, and then 0.75 cos 13.6 for this height here. Okay. The rest you just put in where's the radius of RB and RCB and so on. Then you put in the application of equation. So you put into I and j direction, means you split to x and y. RB, this one. RB here, you split into x and y. So this is x, this is y. So you have a negative component of your x, positive component of your y. So that's why you get negative for your x, positive for your y. Okay. Then you get your RB in a vector form. RBC also same. You split the RBC into x and y. So you have positive x component, positive y component. Same. Okay. Once you get this one, then you put in the acceleration equation. B equal to A plus alpha AB cross R B minus omega squared. So the rest of these two component actually is the acceleration vector. Okay. So alpha R is your tangent direction. Omega square is your normal direction. Again, there's a I write the wrong equation on the whiteboard. I switch. Okay. Okay. Then acceleration at A cannot move. So 0. Okay. If you have pin, straight away 0. Cannot move. Then again, alpha AB. Alpha AB, this is what? Clockwise. So use your hand. You put your hand on the paper there, then you see how your finger curve. This one go in, negative. Okay. Right. Then R, this one you already convert to I and J just now. And then minus omega square. This one same. This one is what? AB. Same. Right? So also negative. Don't put the negative inside here. It means that it's there, right? Okay, so then you get your AB. Okay, for connecting BC, is a general plane motion. General plane motion means it have a rotation and translation. Okay, rod B to have a translation means if this one move, the whole B will move here, and then it will rotate. Okay, so same. If you look at C, you look BC, yeah. So you still use the same equation, you change the notation. So for C, you know that move up positive J in Y direction. AB, B just now, AB, you split into I and J. Just now you find your A already. And then your alpha for B, BC. Here, alpha was anti-clockwise. Your hand point out, right? This one, you hand your thumb point out, so positive, right? So the rest you follow the same. All right, solving, you get alpha. Okay, so today we learned something new, which is relative motion using rotating axis. Previously, your axis, reference axis, your x and x, y prime is the same. Today, we'll try to derive equation when your other object, the axis is moving. For example, previously, your big X and big Y fixed, your X and Y will fix. Today, we learn something new, which is your X and Y, small x, small y axis here, it will rotate. So what happened to the equation? All right. So we'll go very slow on the derivation. Now, this is a big X, big Y mix fixed from observer. So you have every object, rigid body, you have 2 points for sure, always same. Huh? So reference from fixed station to a rotating axis is A, and then B point. So you have RA, RB stroke A, you have vector pointing this way, and then you have a length of YB and XB. Okay. This session, you will learn some a new symbol, also called omega. Previously, you see a W shape, but this one you see like a bell curve, a bell shape. When you see bell shape, it means that you are looking at the axis motion rather than the body motion. Okay, I'll do slowly. So the rest are these we mentioned. So you have two notation. One is big X, one is small x and small y. So we start to derive equation by looking at RB stroke A, this one, this vector. RB stroke A, if you derive it into x and y direction, you'll get xbi, x direction is I. This one, you shift to y direction, you get ybg. Okay. First step, you break this one into x and y. Okay. Then you try to break this one into the same also. So this is a vector triangular. Vector triangular, you know that if you look at vector triangular, we look at resultant. Where is the resultant? This is the resultant point. This is the starting, continue, end point. So this one must be this one plus this one. Right? This is a vector diagram. So you arrive at the first vector diagram. This is what you learn in your early chapter of your chapter 2 or chapter 3. Right? Now, we start to put in angular velocity. We will start to introduce you a new symbol, also called omega, but in a bell curve, bell shape, and acceleration with the dot. So we have angular velocity in bell shape and angular acceleration in bell shape with the dot. Okay. When you see the bell shape of omega, it means you're referring to the axis, axis motion. So velocity, again, you take time derivation, RB, dt, and so on the rest. You get V velocity, and we'll get VB stroke A. We are now focusing on this component first, because this one is more direct. We are focusing, transfer this one into the bell shape omega. So just now we define our RB, this one, in x and y direction. So we can write RB stroke A, we pull to the bracket here. So you write dt xbi plus ybj. So far everything makes sense to you, right? So I pull, continue. Look at this equation. This equation here, you have two vector, two component. You need to use change rules, or the change rules. Means you differentiate this one, you hold this one, plus you hold this one, differentiate this one. You do two set, one set this one, one set this one. You arrive at this equation. Okay, so this one you differentiate, this one you differentiate, you get the first one plus the second set. Okay, then we group them together. We pull this one and this one in the first bracket. We pull this one, put in the second bracket. Okay. So far, mathematics look logic to you, right? Okay. Now, we continue with the mathematics. The first one, the first component of the vector equation here was the velocity of B measured by observer attached to the moving xy coordinate. Okay, so the first one is measured by observer attached to the moving coordinate system. Means you look at here, right? You're focusing on this one. Right. The second one, or we just label this one VBA XYZ. This is the previous what you learned in early section of the chapter 5. Now we look at the second vector you derive mathematically. So this is some changes happen in the field of XYZ coordinate. Means the first one you look at here, second component you observe from the big X and big Y. There's something change if you observe from here. So first component here, this one is a small xy. The second one is a big xy. Okay. Now we start to look at this diagram. This diagram. So we hold this slide and then we look at this small diagram. Now we look at this axis, small x and small y. We try to rotate it. We try to rotate it in a very small angle. We change here. So we rotate your xy a little bit. Okay, a little bit. So enlarge the picture. Okay. So what happened in this picture is that your eye will move to I prime with a small angle. J will move to J prime with a small angle. Same angle, this one same. And then this small tip, the tip here, you need to put in the change of vector, a small change of your eye, so that your vector will reach here. Same with here. Your eye will reach here with dj. Okay, so I become ij with an equation I plus di. So here to change here, you need again is a small vector diagram. This is a resultant. So to get this one, you must take this one plus this one. Same with here. This is your resultant. So to reach your j prime, you take j plus your small dj. Okay. So far everything makes sense to you, right? Okay. Now we move forward. This one is that when you learn a small section of a sphere, this is theta, radian, r, and s. So there's one mathematics saying to find the distance of a small curve, you can use s equal to r theta. Right? So here also same. So magnitude of both di dj here, this one and this one, will equal to 1 theta, d theta, and then the length of I and I prime is so similar that we can write is 1. Here to here actually is 1. Okay. Okay. Then here, because we deal with vector, you look at di. Where di pointing? To y direction, right? This one to y direction. So you can write di in positive j. Where is this dj direction? X direction. But going opposite of your x. So you get negative I for dj. Right? Okay. So you can write your equation. I di dt you can write as delta dt. Here, this small di is so small that is same with your d theta. This small di is the same with theta. So you can write di equal to d theta. Why j here? Because this di is in y direction. So you get positive j. What is the d theta dt? Omega. What is d theta dt is omega. Same with j. dj dt, what is your j here? dj here is the same as your d theta. However, the direction of this dj is opposite of your x, so it's minus I. Again, d theta dt, you get omega, so you get minus d omega. Okay, now use your right hand rules. I is omega j. Your I is your omega j. So again, your thumb is the final answer. If your di is in I direction, and your right hand rules always take omega r, right? Omega r. So here, we get this one. Di equal to omega cross I. So you take this one, omega cross I. What is about your j? Your j is omega cross j. But this one, you look at the slides later. Too many mathematics calculation. I'll go very fast here. The rest you extract from the graph. Go very fast. This one you read. At the end, you reach this one. The equation above. This one is previously we learned earlier. You compare side by side. When you look at the axis, something appeared at the back of the equation. When you look at the rotating axis, you need to add plus something at the back. Okay. Acceleration also same. Acceleration also same procedure. I will not go deep into detail. You look at the diagram, look at my slides, and then you read at your study time. So same. This one, in fact, in the canvas also, appendix. At the end, you reach this acceleration equation. You reach this acceleration equation. It's fixed already, so you only need to memorize this equation. Okay. And yeah, okay, let's directly look into the example. So you're given an object. Now you have one moving object on the rigid body. You have two objects now. You have two objects now. Previous example 10 and before, you only see one rigid body. Now you see two rigid body. You have a ring at the end of the rod here that is moving in 3 meters per second square and 2 meters per second square. So at instant 60 degree, the rod has an angular velocity 3 radian per second. Acceleration also given. At this instant, collar C travel outwards along the rod. When x equal to 0.2 meter, velocity is 2 meters per second square. All right, acceleration is 3. Both measure relative to the rod. Determine the Coriolis acceleration and the velocity acceleration of the collar at instant. What is Coriolis? This one. Coriolis acceleration is this term. So how do we solve this kind of question? When the question purposely mentioned you need to solve Coriolis, means you need to memorize this whole equation. Okay. I will not give you the equation. You need to memorize. I will let you know. Okay. So as you can see here, we straight away you write the you just memorize lah. Actually, it's just standard equation. You just memorize the whole thing. You just memorize. So you modify based on what you see. You just memorize. You memorize the purple color. You look at the diagram, you modify accordingly. For example, first equation is B and A, but here you look at C and O. So you modify your C, your B to C, A to O. Then same with the acceleration. You change all the term inside the equation. The rest is same. So this table will be given in the, if this question come out, there will be this table given to you. So you just refer to this table and then substitute accordingly. Okay, you just substitute accordingly. Okay, this slide you go home and read about it lah. Read about it. Okay. Then you can find the answer. Okay, the last example for this chapter is this one. This question come out once in for this module, come out once in final exam. Okay. So you have two planes there. One in the circular motion, one is a linear motion. Then you are given the reference plane, x and small x, big Y and small y. Have the same elevation means they are moving at the same plane. It's a two-dimensional question. Have the motion shown in the figure, determine velocity and acceleration of A as measured by pilot B. It's a relative motion. It measured by pilot B. So your equation will be seeing is R, A stretch B. Okay. So coordinate axis. Okay, so you use this equation. VB equal to VA, then VB stroke A. You put in all this equation, and again, you memorize this equation. You modify accordingly. This is BA, because this case is asked you from B. You need to modify this equation. The question asks you measured by B to A. So you change this one, you flip this one. B stroke A means you measure from B. Measure from A. But here you measure from B, you flip this one. A. Same with here. Once you do, you write them in the vector form. VB in J, you can see here, this is a circular plane B in a circular motion going up Y, positive J. And here you use the tangent acceleration V squared over rho. Rho is given. VB is given. So you find what is your VB. Same with tangent. So acceleration always have tangent and normal direction, right? So you put in accordingly. Normal you find, tangent already given. Tangent acceleration go back from your Y, so negative 100. This is omega. No, this one is rigid body, but it's moved in the curvilinear motion. This is just the first step because here you need to find the relative position later. This is just an early calculation. Later you substitute back here. So here you substitute back, you get omega. Okay. So here, this example, we put it in hour because we don't want to put in the meter per second. We just follow the unit. Okay. So here, once you find the omega and it is clockwise, so use your right hand rules. Is clockwise means clockwise means going in, right? clockwise means going in, so negative. Okay. So once you have this one, you just substitute everything there. Okay. So the rest, you just look at the screen, substitute, and you find the answer. Okay. So with this, we conclude chapter 5. Okay. So we have a short break. We continue 11. Then we go into chapter 6.